In this video, we are going to talk about categorizing our isolated singular points into one of three types: a pole of order m, a removable singular point, or an essential singular point. This is our overview slide, which we'll spend about 5 minutes on before we go over each topic in more detail and with more examples. We will be using our Laurent series to help us categorize our singular points. To review, if f has a singular point at z0, then f of z has a Laurent series representation, which looks like this: summation n equals 0 to infinity an z minus z0, z0 being our singular point, raised to the n. And this is the analytic part. And then we have plus our principal part, which looks like summation of bn z minus z0 to the negative n. Written out in this way, it's b1 over z minus z0 to the first power plus b2 z minus z0 to the second power up to bn z minus z0 to the nth power and possibly out to infinity. If our Laurent series takes this form, that is, the principal part contains at least one non-zero term, but the number of such terms is only finite and equal to m over here, then we say that the singularity is a pole of order m. And if we have a pole of order m equals 1, we call it a simple pole. We have this example of a simple pole where we have a function. We take the Laurent series expansion, and we see the Laurent series expansion has 1, 2, 3 terms, and only one term in the principal part. The coefficient on this is m is equal to 1, so we have z equals 2 is a simple pole where m is equal to 1, and the residue at z equals 2 is equal to 3. If our Laurent series expansion has this form here, in other words, every coefficient b sub n is 0, there's no principal part, then we call our singularity a removable singular point. It is called removable since we can take or redefine f at z0 so that f at z0 equals a0. Then the expansion becomes valid throughout the entire disk, and the singularity z0 is therefore removed. An example here is 1 minus cosine z over z squared. We can see the singularity at z equals 0. We can take the Laurent series expansion, and we see we get no principal part. So z0 then is removable, and the residue at z equals 0 is equal to 0. Finally, we have, if the principal part has an infinite number of coefficients, we call that an essential singular point. And our example is e to the 1 over z. When we expand this out, we get 1 plus 1 over z plus 1 2 factorial z squared plus 1 over 3 factorial z squared, and it keeps going to infinity. So here we see z equals 0 is an essential singularity with residue equal to 1. So the three types of singularities all depend on the principal part. We have three possibilities for the principal part. Either we have no terms in the principal part, a finite number of terms, or an infinite number of terms. If we have no terms, we have a removable singular point. If we have a finite number of terms, then we have a pole. If we have an infinite number of terms, then we have an essential singular point. We have this one other topic, which is residues at poles. So rather than calculate the entire Laurent series for some functions, if we have a pole, then we can use this theorem to get the residue in a more simple way. So the theorem says an isolated singular point z0 of a function f is a pole of order m if and only if f of z can be written in the form f of z is equal to phi of z over z minus z0 to the m, where phi of z is analytic and non-zero at z0, then the residue at z equals z0 is equal to the mth minus 1 derivative of phi evaluated at z0 divided by m minus 1 factorial. And we'll see this theorem and some examples. That concludes our overview, so we'll go back and look at our topics in more detail. First, we have our Laurent series. So if we have a function f, If it has a singular point at z naught, in other words, a point where it's not defined, then f of z can have a Laurent series representation where we represent f as a polynomial. And the polynomial has an analytic portion, which is the summation n equals 0 to infinity a sub n z minus z naught, this z naught being the singular point, raised to the n, plus the principal part. And this is the part where we take into account that f has a singular point, and that's b1 over z minus z naught, plus b2 over z minus z naught squared, up to bn over z minus z naught to the nth, and it can go on to infinity. And it is this principal part which will help us classify our isolated singular points. If the principal part has no terms, we have a removable singularity. If it has a finite number of terms and the number of terms is m, then we have a pole of order m. If it has an infinite number of terms, then we have an essential singularity. We are going to start here with the pole of order m, where we have a finite number of terms. The definition of a pole of order m, the principal part contains at least one non-zero term, but the number of such terms is only finite. And if the number of terms is m, the expansion takes this form. We have our analytic portion, and our principal part only has m non-zero terms. And a pole of order m equals 1 is referred to as a simple pole. Our first example is the function z squared minus 2z plus 3 divided by z minus 2. You can see we have a singularity at z naught equals 2, which means we want to expand this function then in the Laurent series around z naught equals 2. To expand around z minus 2, since z naught is equal to 2, I need all my z's in terms of z minus 2, not just these plain z's. Well, here I can factor out a z minus 2, so that's good. I still have this z to deal with, but for now let's do a little bit of algebraic simplification and we'll deal with the z next. So first let's do the cancellation. So we have z plus 3 over z minus 2. This term looks good. It looks just like this form, where z minus 2 and then our b1 is equal to 3. But we still need to take care of this z. But I can just subtract a 2 from this z and then add a 2. And this is now exactly in Laurent series form. Remember, this b1 is equal to 3, and then we have z minus 2. We have a to the n. It looks like the first coefficient for n equals 1 of our analytic part is 1, and then we have z minus 2 to the 1. And then for a naught, we have an is equal to 2. And here n is equal to 0. So this here, again, is our Laurent series. And you can see that we have, in the principal part, we have exactly one term, which means m is equal to 1, which makes z equal to 2 a simple pole, and the residue at z equals 2 is our b1 coefficient, which is equal to 3. For our next example, we have sinh of z over z to the fourth, and we can see that this has a singularity at z equals 0. So what we need is a Laurent series expansion at z equals 0. This z to the fourth, well, that's in the z minus 0 or z minus z naught form, so that's good. But we need to expand sinh of z into a Laurent series. And what we will use are these formulas here that we developed when we were talking about Laurent series. And these actually will become useful in this chapter. You might want to write them down somewhere so you remember. So sinh is equal to summation n equals 0 to infinity, z raised to the 2n plus 1 divided by 2n plus 1 factorial, and cosh is equal to summation n equals 0 to infinity, z to the 2n divided by 2n factorial. Using then this sinh, we factor out our 1 over z to the fourth, and we get our summation z equals 2n plus 1 over 2n plus 1 factorial. I expand out this summation, so I plug in n equals 0, and I get z to the 1 factorial, which is just z. For n equals 1, I get z to the third over 3 factorial. For n equals 2, I'm going to get z to the fifth over 5 factorial, and the pattern continues And now I'm going to multiply in my 1 over z to the 4th. So here z cancels with one of these, so I get 1 over z to the 3rd. Over here my z cancels with 3, so I get 1 over 3 factorial and 1 over z. Over here, this gives me my first positive exponent, z over 5 factorial, and the rest we have more positive exponents. This is the analytic portion after this z. We can see then our highest exponent in our principal part is this 3, which means z equals 0 is a pole of order 3, and then the residue of z equals 0, that's this coefficient at z to the negative 1, that's 1 over 3 factorial. Our next example is 1 over z squared times 1 plus z, and we can see that this function has singularity at z equals 0 and z equals minus 1. I will start with the singularity z equals 0, so I'll need to expand our function into a Laurent series centered around z equals 0. So this z squared is in correct form, so we can factor that out, and then we have 1 over 1 plus z left, but I'm going to use this formula here, this series formula, in which case this 1 over 1 plus z is going to become 1 over 1 minus negative z. Now plugging a negative z instead of z into this formula, I still have my 1 over z squared summation negative z to the n. Plugging in values for n into here, I still have my 1 over z squared. When n equals 0, I get 1. When n equals 1, I have minus z. When n equals 2, I have positive z squared. When n is equal to 3, I have negative z cubed, and the pattern continues. Multiplying in my z squared, then I get 1 over z squared. Here I get minus 1 over z. Then I get a plus 1, and then minus z plus z squared. The rest of this is all analytic. So these two terms here, the first two terms, are my principal part. And we can see the largest exponent for our principal part is this 2. So m is equal to 2. So for z equals 0, we have a pole of order 2, and the residue is equal to our minus 1. We have our next singularity, z equals minus 1, and we are going to do this later in this video because the Laurent series centered around z equals minus 1 is a little, I don't know, it just has a lot of algebra. So there's a theorem that we are going to use to make our life a little bit easier. So we're going to postpone this part of the problem. The next type of singularity is a removable singular point where every coefficient b naught is equal to 0, so there's really no principal part. Our example is 1 minus cosine of z over z squared, and we can see we have a singularity at z equals 0. When we expand this out around z equals 0, first we can factor out the 1 over z squared here. And then we still have 1, and then we're going to expand our cosine of z using this series here that we found when we worked on Laurent series. So we have the summation n equals 0 to infinity, negative 1 to the n, z to the 2n over 2n factorial. Expanding our summation now, we still keep our 1 over z squared. We still keep this 1. When n is equal to 0, we get negative 1 to the 0, which is 1, times 1 over 1. So this is 1, but remember, we have a negative sign in front of the summation, so this becomes minus 1. So these two 1s are going to cancel. When n is equal to 1, we get a negative 1 times this negative 1 gives us a positive, and then we have z squared over 2 factorial. When n is equal to, what was this? This was 0, 1. When n is equal to 2, we get a positive, but with this we get a negative. Then we get z to the 4th over 4 factorial. When n is equal to 3, we get a negative, but this is negative, so we get a positive. Z to the 6th over 6 factorial. The pattern continues. Again, these two cancel out. So when we multiply in by the 1 over z squared, these cancel and we get 1 over 2 factorial. Then we get 1 over 4 factorial z squared plus 1 over 6 factorial z to the 4th. The rest of all of this is analytic. And in fact, this whole thing is analytic. We do not have any z's in the denominator. So the principal part is equal to 0. So z equals 0 is removable, and the residue z equals 0 is equal to 0 because b1 is equal to 0. And another fact, the residue at a removable singular point is always 0. And that's kind of expected, since if it's removable, that means the principal part is 0, which means b1 is equal to 0. So this is totally expected. Another point, no pun intended, is that this singularity, a removable singularity, is called removable since we can define or redefine f at z naught so that f of z naught is equal to some value a naught. Hopefully it's equal to the limit of f of z as z approaches z naught. And then the expansion becomes valid throughout the entire disk, and the singularity z naught is therefore removed. So in our example here, and defining then 1 minus cosine of z over z squared as the limit as z approaches infinity. And remember, we want to define it as the limit so that it's continuous and analytic. Well, here when we plug in 0 into the numerator and denominator, we get 0 over 0, which means we can use L'Hopital. And we can say that's equal to the limit as z approaches 0 of, on top we have a positive sine of z over 2z, taking the derivative of the top and bottom. And now plugging in 0, we get 0 over 0. So again, we can use L'Hopital. So that's equal to the limit as z approaches infinity. Derivative of sine is cosine. Derivative of 2z is equal to 2. Plugging in 0, we get cosine of 0 is 1 over 2. So we would define our function at z equals 0 to be equal to 1/2. And in that way, we will have an expansion that's valid throughout the entire disk, and in effect, we have removed our singularity. Our last type of singularity is the essential singular point. An essential singular point is one where the principal part has an infinite number of coefficients bn that are non-zero. Our example is e to the 1 over z, which you can see has a singularity at z equals 0. Our e to the z has this summation formula over here. It's exactly the formula we have. So we have n equals 0 to infinity, 1 over n factorial, 1 over z to the n, which looks like this over here. You can see there's the 1 that's analytic, but everything else is principal part. And the principal part is infinite, which means that z equals 0 is an essential singularity, and the residue at z equals 0 is equal to 1. So now we've looked at the 3 types of singularities. We have this last topic which pertains to poles of order m, and it makes finding the residue sometimes easier. It's this theorem here which has this really intimidating looking form, but it's actually really easy when it is useful. So let's take a look at this theorem. The theorem says isolated singular point z naught of a function f is a pole of order m if and only if f of z can be written in this form. F of z is equal to phi of z over z minus z naught to the m, where phi of z is analytic and non-zero at z naught. And then the residue will be equal to the m minus 1 derivative of phi at z naught divided by m minus 1 factorial. Sometimes people like to separate this theorem into 2 parts. They talk about the residue when m is equal to 1, and then they talk about the residue when m is greater than or equal to 2. But this formula combines both. The only thing you need to remember when you use this formula is that if m is equal to 1 and then you get a 0th derivative, that's just the function evaluated at 0. Anyway, this theorem provides an alternative characterization of poles and a way of finding residues of poles that is often more convenient. The first example we are going to do is this example here, 1 over z squared times 1 plus z, which has singularities at z equals 0 and z equals negative 1. So we have done this example for z equals 0. We wrote out a Laurent series expansion. We found that 2 was our greatest principal part exponent. So we said that z equals 0 is a pole of order 2. We found the residue then was equal to negative 1. But now when we look at z equals negative 1 of the function 1 over z squared, 1 plus z, this is a little more difficult to put in a Laurent series expansion centered at z equals negative 1. You can try it, but it's kind of ugly. So what we're going to do instead is use this theorem here. We start by pulling out our singularity, our z minus our singularity, that is z minus negative 1, that's z plus 1. And the rest of the function we're going to call phi of z. So in this case, phi of z is equal to the z to the negative 2. So you can see now we have this form here. F of z is equal to z to the minus 2, or 1 over z squared, times our z minus z naught to the m. That is z minus negative 1 to the first power. Here m is equal to 1. To use this theorem, we need to verify that phi of z is analytic and non-zero at z naught. So phi at negative 1, when we plug that in, we're going to get 1 over negative 1 squared. So it's analytic and it's not equal to 0. So we can use this formula. Plugging in then for the residue, phi of m minus 1. Again, m here is equal to 1. So this is phi to the 0th derivative, which is just the function phi evaluated at z naught. And we've already seen that phi at negative 1 is just 1 over negative 1 squared, which is just equal to 1. And then we put that over m minus 1 factorial. And when m is equal to 1, that's 0 factorial, which is just equal to 1. So finally, 1 then is our residue. So z equals minus 1 is a simple pole with a residue equal to 1. And just to illustrate, I can actually redo my z equals 0. I can actually recalculate the residue based on this theorem here. So I'm going to redo z equals 0 using my theorem. So I have 1 over z squared, 1 plus z. And I want to rewrite this as phi of z over my z minus 0 squared. So phi of z then is going to equal to, so here's my z squared, so what I have left is 1 over z plus 1. And when I plug in 0, my z naught, my singularity, I see that my function is defined, it's analytic, and it's not equal to 0. So I can use this theorem now. Then looking at this theorem to calculate the residue, in this case m is equal to 2, I'll need to find the first derivative of phi. So rewriting phi of z as 1 plus z to the negative 1, I can find the derivative is negative 1 plus z to the minus 2, or negative 1 over 1 plus z squared. Which means my residue at z naught equals 0 of f of z is equal to the first derivative of phi evaluated at 0 divided by 2 minus 1 factorial. 2 minus 1 factorial is just 1, so I get phi prime of 0, which is equal to negative 1, which is the same residue that I found using the Laurent series expansion. So for poles, this does not work. This theorem does not work for removable singular points or essential singular points. But for poles, you can either write out the Laurent series expansion to figure out if it's a simple pole and the residue, or you can use this theorem here to figure out what the pole order is as well as the residue. We will do another example using this theorem. F of z is equal to z plus 1 divided by z squared plus 9. We will start by factoring out our z squared plus 9 into z plus 3i, z minus 3i, so that we can note that f of z has singular points at z equals 3i and z equals minus 3i. So for our first pole, z equals 3i, f of z is equal to phi of z over z minus 3i, where phi of z then is whatever's left over if we take out the z minus 3i. So we have the z plus 1, z plus 3i, and we note that phi of z is analytic at z naught equals 3i, so when we plug in 3i, we don't get a singularity, and also when we plug in 3i, we don't get 0. So we can now apply this theorem, and we can say that 3i then is a simple pole. And its residue, well, since it's simple, m is equal to 1, so that just means it's our phi evaluated at 3i over 1 minus 1 factorial, which is just 0 factorial, which is 1. So we're left with phi of 3i. So plugging in 3i into phi, we get 3i plus 1 over 3i plus 3i, which is 6i, which gives us 1/2 minus 1/6 I. One thing I'm just going to warn you about, when you plug in your phi of 3i, just make sure you're not plugging 3i into your f of z. Make sure it's plugged into your phi of z. I kind of shrank my z equals 3i to give myself some space for z naught equals minus 3i, the other singularity. Now f of z is equal to, well, on the bottom we're going to have our z minus z naught, so z minus negative 3i or z plus 3i. And on the top we have phi of z, so that's whatever is left after we take out our z minus z naught. So what's left is z plus 1 divided by z minus 3i. And again, we note that phi of z is analytic and non-zero at z naught equals 3i. So when I plug in 3i, I get something that's defined and it's not equal to 0. So I can use my formula. The residue then is equal to phi of 3i divided by 1 minus 1 factorial, which is phi of 3i, which is equal to my 1/2 plus I over 6. Our next example is f of z equals log of z raised to the third divided by c squared plus 1, where the branch log of z equals natural log of r plus I theta, where r is greater than 0 and theta is between 0 and 2 pi, is the branch we're going to use. We want to find the residue at z naught equals I. We start by factoring the denominator, so we get z plus I and z minus I in the denominator, so we can identify our simple poles are at z equals minus I and z equals I. For z equals I, then, our f of z is equal to phi of z over z minus I, where phi of z, then what's left, is our log z cubed over z plus I. And we note that phi of z is analytic and not equal to 0 at z equals I. We can plug in I and we're good. Plugging then into our residue formula, we have, well, here m is equal to 1. So we just need not the derivative, but phi at z naught. So we have phi of I divided by 1 minus 1 factorial. That's just 0 factorial, which is 1. So we have phi of I, which is equal to log of I to the third over 2i. So I rewrote I in exponential form. So that's log of e to the I pi over 2 over 2i, which is equal to natural log of 1 plus I pi over 2 raised to the third divided by 2 pi. To go from here to here, I used our logarithm formula from the chapter or video when we did logarithms. So the log of r e to the I theta is equal natural log of r plus I theta. And this I, 2 pi n, that's in case you're on the wrong branch, but we're not going to be. So r is equal to 1 here, so we have natural log of 1 plus I pi over 2 raised to the third over 2i, and we're in the correct branch because pi over 2 in this case is between 0 and 2 pi. So we're good. We don't need this extra I 2 pi n. Here then, natural log of 1 is 0. We have I to the third, which is negative I. Then we have pi over 2 to the third over 2i, which is equal to negative pi to the third over 16. Our next example is f of z equals sinh of z over z to the fourth. If you recall, we had already done this earlier using a Laurent series expansion, but let's try using this theorem now. We see that sinh of z over z to the fourth has a pole at z naught equals 0. We will then write f of z equals sinh of z over z to the fourth is equal to our z minus z naught to the fourth times phi of z, where phi of z is equal to sinh of z. But what we see is that sinh at 0 is equal to 0, so we cannot use this formula above, or this theorem above, because the condition is that phi of z must be non-zero. So this is an example where you would have to write out the Laurent series expansion in order to solve this problem. And we've done this before, so I have this for your reference, but you can go back in the video if you need explanation. Our last example before we do some review problems is f of z equals 1 over z times e to the z minus 1. And we can see that this function has a pole at z equals 0. and I don't know if you want to take a guess, is this pole of order 1 or 2? And I'd kind of say 1 because it has z equals 0, and then it also has this problem at z equals 0 here. But let's take a closer look. If I just try to single out this z over z minus 0 squared, phi of z, I still have my function, my phi of z then is going to equal to 1 over e to the z minus 1. When I plug in 0, I'm still going to have a singularity. In other words, f of z is not going to be analytic. So I'm going to need some sort of hybrid approach. Looking at my denominator, just my denominator for a moment, z times e to the z minus 1. So I have z, and then I'm going to expand out my e to the z using this formula here. So I have my z times 1 plus z plus 1 over 2 factorial z squared plus 1 over 3 factorial z to the 4th on to infinity. And then at the end of my series, I'm going to have a minus 1. So these ones cancel. When I multiply my z in, I get a z squared times 1. And then I have a 1 over 2 factorial z plus when I have this, I have my 1 over 3 factorial. I have a z to the 4th, but I factored out a z squared. So 1 over 3 factorial z squared plus 1 over 4 factorial z cubed. Now I can find my f of z is equal to phi of z over z squared. Remember this line here, this, I'm going to underline it in blue. This expression here is my denominator of my f of z. So f of z now, if I have this on the bottom, I'm going to factor that out. So all this here becomes the rest of my phi of z. So my phi of z is this factor, this sum, to the negative 1. Which means my phi prime of z, I multiply by negative 1, I have my sum to the negative 2 times the derivative of what's inside. And when I calculate then my residue at z equals 0, then phi prime at 0, plugging in 0 here, over, and now because m is equal to 2, I need my 2 minus 1 factorial, so I get phi to the 0 over 1, which is just phi to the 0, which is equal to, plugging in phi prime of 0, plugging in, I'm just going to get that's equal to 1/2. This is all 0, this is all 0 on the bottom, so I have a negative 1/2. We've covered all our material, so I'm going to do a quick review, and then I'm going to give you a few problems for you to try on your own, and then I'll give you the solutions. But first, let's quickly review what we covered. We started with a review of a Laurent series, so f has an isolated singular point at z0, then f of z has a Laurent series representation centered at z0, which looks like this, an analytic part and a principal part. We use the principal part to classify our singular points. So we have a pole of order m when the principal part contains at least one non-zero term, but the number of terms is finite, and if it's equal to m. The form, when we have a pole of order m, our Laurent series looks like this. It has our analytic part, and then b1 over z minus z0 plus b2 over z minus z0 up to bm over z minus z0 raised to the m. And we have our first example. We talked about a removable singular point. So if every coefficient in b0 is 0, so the principal part is equal to 0, our Laurent series takes this form, and we call our singular point removable because we can redefine f at our singular point to be equal to a0, and therefore we can make our function analytic throughout the disk, and the singularity is therefore removed. We have our example of a removable singular point. The last type of singular point we have is the essential singular point, where the principal part has an infinite number of coefficients that are non-zero, and this was our example. Finally, we talked about for poles, and this theorem only works for poles. It does not work for removable singular points or essential singular points. We have this theorem which gives us an alternate way of finding the residue. So often you have a choice of either doing the Laurent series expansion or this theorem, but there are cases where this theorem is you can't use it because you do need this condition here met. The phi of z is analytic and non-zero. For review, I have these 4 problems for you to try. And here I have the problem typed out and then I just wrote it out just because. So there are 4 problems. The first one is to classify the singularities of A, 1 over z squared times 1 plus z, B of sine of z over z squared, and C of z plus 3 over z minus 8 squared times z minus 2 times z plus 1 cubed. And then the second problem is to find the residue of z cubed plus 2z divided by z minus I cubed. So I suggest you pause this video, give them a try, and then come back and I'll have some solutions. This first problem, I just realized we worked this problem in the video, so I won't give any explanation, but here it is, one way to work this problem. This next problem, you can see the function sine z over z squared has a singularity at z equals 0, so I wrote out a Laurent series expansion centered at z equals 0. I started by factoring out my z squared, and then I used my summation formula here for sine of z, and I replaced sine of z with a z minus 1/3 factorial, z cubed, and you can see the rest. I can then have my Laurent series expansion, and I identified here is my z to the minus 1 term, so my residue is equal to 1. Oh, and actually I need to classify the singularity. So in this case, looking at my principal part, which is only this 1 over z, everything else over here is analytic. So the largest negative exponent is equal to 1. So we have a simple pole at z not equals 0. For part C here, remember we only have to classify the singularity. It did not ask us to write the residue. But here we have a bunch of poles, 3 poles, singularities at z equals 8, z equals 2, and z equals negative 1. And I use this theorem for the poles that says the isolated singular point of a function is a pole of order m if and only if f of z can be written in this form where phi of z is analytic and non-zero. So for z naught equals 8, our singularity at 8, f of z is then equal to phi of z over z minus 8 squared, where phi of z is equal to our z plus 3 and over z minus 2 times z plus 1 cubed. I verify that phi of 8 then is analytic and non-zero. Write the conditions here. So what I have is phi of 8 is equal to 8 plus 3 is 11 over 8 minus 2 is 6, so I did my subtraction wrong. This should be 6, and then 8 plus 1 is 9 cubed. So we see that this is analytic and not equal to 0, which means then this m here, this 2, is the order of our pole. So z naught equals 8 is a pole of order 2. You can do similar work to show that z naught equals 2 is a simple pole and z naught equals negative 1 is a pole of order 3. You can further go on and calculate the residue for each of these poles, but because there were so many factors here, I didn't really want to calculate the derivative, so I skipped calculating the residue since the problem only asked me to classify the singularities. This next problem, we were asked to find the residue of z cubed plus 2z over z minus I cubed. And this problem, I chose to use this theorem. It seemed to be working for me. So you can see our singularity as at z equals I. And so our f of z is equal to phi of z over z minus I cubed, where phi of z is equal to z cubed plus 2z. When we plug in our z naught into phi, that is phi of I, we see that it's analytic and non-zero. So what we have then is a pole of order 3, and then to calculate our residue, since we're at 3, we need the second derivative of phi. So I took the first derivative of phi and got 3z squared plus 2. The second derivative then would be 6z, and when I plug in I get 6i. So z equals I is a pole of order 3 with residue. Now we have our 6i divided by 3 minus 1 factorial, which is 2 factorial, which is just 2. So here is our residue. And that wraps up this video. Thank you for watching.